All right, another issue that we want to make sure that we think about each time we introduce a new kind of supervised learning representation is to ask what its preference bias is. So Charles, can you remind us what preference bias is?
Like restriction bias tells you what it is you are able to represent. Preference bias tells you something about the algorithm that you're using to learn that tells you, given two representations, why it would prefer one over the other. So perhaps if we think back what we talked about with decision trees, we preferred trees where nodes near the top had high information gain. We preferred correct trees. We preferred trees that were shorter to ones that were longer unnecessarily, and so on and so forth. So that actually brings up a point here, which is we haven't actually chosen an algorithm. You talked about how derivatives work, how backpropagation works, but you missed telling me one very important thing, which is how do we start? You tell me how to update the weights, but how do I start out with the weights? Do they all start out at 0? Do they all start out at 1? How do you usually set the weights in the beginning?
Yes, indeed. We did not talk about that. It's really important. You can't run this algorithm without initializing the weights to something, right? We did talk about how you update the weights, but they don't just, start undefined and you can't just update something that's undefined. So we have to set the initial weights to something. So a pretty typical thing for people to do is small random values. So why do you suppose we want random values?
Because we have no particular reason to pick one set of values over another. So we start somewhere in the space. Probably helps us to avoid local minima.
Yeah, kind of. I mean, there's also the issue of, well, if we run the algorithm multiple times, if it gets stuck, we'd like it to not get stuck exactly there again if we run it again. So it gives some variability, which is a helpful thing in avoiding local minima. And why do you suppose it's important to start with small values?
Well, you just said in our discussion before that if the weights get really big, that can sometimes lead to overfitting because it lets you represent arbitrarily complex functions.
Good. And what does that tell us about what the preference bias is then?
Well, if we start out with small random values, that means we're starting out with low complexity. So that means that we prefer simpler explanations to more complex explanations. And of course, the usual stuff like we prefer correct answers to incorrect answers and so on and so forth.
So you'd say that neural nets implement, or maybe we should say that neural networks implement a kind of bias that says prefer correct over incorrect, but all things being equal, the simpler explanation is preferred.
Well, if you have the right algorithm, if the algorithm starts with small random values and tries to stop, and when you start overfitting, then yeah, because you're going to start out with the simpler explanations first before you allow your weights to grow. So yeah, I buy that.
So this is reminiscent of a principle that's known as Occam's razor, which is often stated as entities should not be multiplied unnecessarily. And given that we're working with neural networks, there's a lot of unnecessary multiplication that happens. But in fact, this actually is referring to exactly what we've been talking about. So this unnecessarily is one interpretation of this is that, well, when is it necessary? It's necessary if you're getting better explanatory power. You're fitting your data better. So unnecessarily would mean, well, we're not doing any better at fitting the data. If we're not doing any better at fitting the data, then we should not multiply entities. And multiplied here means make more complex. So don't make something more complex unless you're getting better error. Or if two things have similar error, choose the simpler one. Use the one that's less complex. That has been shown to, if you mathematize this and you use it in the context of supervised learning, that we're going to get better generalization error with simpler hypotheses.